Yeah, so it's a continuation.
Huh? That's fine. Is there a chat here?
Yeah, there's
Like, where is the chat? Can somebody give us a thumbs up on Zoom if you can hear us? Okay, thank you, Nicole. All right, and you can see the screen too, the screen, the slides and me. Okay, all right, we'll get started as soon as we can get the room to.
I finally see where the chat is.
Oh, the chat's there. Okay, yeah, the chat's on the other screen.
Sorry, guys.
There we go. Okay.
Okay, everyone, LaShawn's gonna start here in just a moment.
All right, so everybody enjoyed your break and your coffee break. It was nice hearing from John about the COVID update. So I'm excited to be able to share with you some of the preliminary results we have on evaluating a shortened fit test method for half mask respirators using the OHD QuantiFit. This has been a long time coming because we originally started this research in January of 2020, and then everybody knows what happened, and the IRB will shut you down from human studies research in the middle of a pandemic. So we had a long pause, and we were able to start back this last August. And I was really hoping we would have this study completed, but we've got just a few more fit tests. We're actually finishing up this week and early next week. So I'm going to show you what we have so far as results. So slide advance. There we go. All right, so you all know that if you're an employer in the United States and you have employees that you require to wear a tight fitting respirator, you have to fit test them at least annually. There are two protocols that are accepted by OSHA. And so you hopefully are familiar with both of them. So I'm going to tell you just a little bit about both of them in detail so that we'll be clear on what we're talking about. So the one protocol is using ambient aerosols. So is anybody in here familiar with the Porticount instrument? So you've used a Porticount before. So that uses ambient aerosols. It's CNC condensation nuclei counter. And so what the Porticount instrument does is it calculates the concentration of particles outside the respirator, and then it calculates the concentration of just ambient particles inside the respirator, and it calculates a fit factor by taking the ratio of the concentration outside versus the concentration inside. There is another protocol that's accepted that is controlled negative pressure. And this is the QuantiFit instrument that is manufactured by OHD. Is anybody in the room familiar with the QuantiFit? Okay, we've got a few. So the QuantiFit, it calculates the fit factor differently. And it was actually the QuantiFit that we used in our study. So with the QuantiFit, it actually uses air as the challenge agent. And so it's measuring the leak rate into the respirator directly. And what it does is it pulls a negative pressure on the mask, and it pulls a challenge pressure of 15 millimeters of water, or 0.58 inches of water, if you like inches better than millimeters. And this pressure is designed to replicate the mean inspiratory pressure of 53.8 liters per minute that would cause a leak under normal conditions. And so it pulls this constant pressure on them, or this negative pressure on the mask, and then the subject will hold their breath, and the instrument will measure the rate of airflow it has to exhaust from the mask in order to keep that negative pressure, so constant negative pressure. And then the QuantiFit calculates the leak rate just differently from the port account. So it takes that mean inspiratory flow rate of 53.8 liters per minute, and then the leak flow rate that the instrument measures, and it calculates the fit factor. So both instruments are measuring fit. The QuantiFit measures the leak rate directly, and they calculate their fit factor just a little bit differently. So I wanted to clarify that point. So there are two protocols that are currently accepted with OSHA is using controlled negative pressure. So the first one is the reference method that several of us in the room, I'm sure, have used before. It takes 4 forevers in a day because there are 8 exercises. So about 9 minutes if everything goes well. And the reference method, just to remind us, it has all of these different steps. So with the QuantiFit, you will perform the exercise. And so we have normal breathing, deep breathing, head side to side, head up and down, talking, bending over, and then normal breathing. You'll perform those for a minute. And then at the end of that, you'll hold your breath, and the instrument will take a measurement of the leak rate. There's also a grimace exercise. We don't measure a fit factor for that particular exercise because it's designed to try to break the seal of the mask and then get the seal to come back. So the reference method is approved by OSHA, and then we also have the read-on method. So the read-on method is a shortened method. It has 3 different exercises. So you face forward, you bend over, and then you shake your head from side to side. And I love this exercise. This is so fun when you are doing fit testing in a university and you're instructing your participants to shake their head back and forth vigorously while shouting. You get a lot of looks from people walking by. But those are our 3 exercises. So you do that for 30 seconds, and then the instrument takes the measurement of fit. And then you do 2 redonnings of the respirator. The redon method, if I remember correctly, came out in about 2016. And it was based on research that showed that it was actually redonning of the respirator and having the subject take it off and put it back on correctly that showed a better measure of fit than all of those different 8 exercises. So the read-on method, if everything goes well, takes about 3 minutes. But if you're in industry, time is money. And so because we have to perform so many fit tests annually, if we can reduce the amount of time that's required to perform a fit test, everybody would be happy. The employer would be happy, the employee would be happy. So a reduced amount of time required would benefit everyone. And so that's the purpose of this study. So we wanted to investigate whether a modified read-on protocol would be as effective compared to the reference method. And specifically for this particular study, we're focusing on half-mask respirators. And so the modified read-on protocol is really, it's just the same protocol, except we eliminated those 30 seconds of exercises. So instead, we've just got these same static positions. They face forward, hold their breath, and take a measurement of leak. Bend over so you're facing the floor and take a measurement. And then we still do the shaking your head from side to side and shouting, but it's only for about 3 seconds, and then take a measurement of leak. And then the 2 read-on steps remained. So this study was the design and the methodology is based on ANSI requirements. So ANSI actually specifies the criteria to evaluate a new fit test method in Z8810. That was last updated in 2010. And so what they say that you have to do is you do sequential paired fit test. So during the same dawning, you compare your new method that you're proposing with the reference method. So we have to go back and compare it to that 8-step reference method. ANSI requires that you have to have at least 100 of the paired tests, and you have to have at least 25 different test subjects, so at least 25 participants. They don't specify how many respirator makes and models that you have to use. They just say you need a variety. And then the big one, and the one that's been the most challenging for us, is at least 50 of those paired fit tests have to be a fail for the reference method. And so that is the methodology that we used, is the one that's specified by ANSI. So we recruited test participants from the population at the University of North Alabama for this study. It was open to students, faculty, staff, but of course we got all students. They didn't have to have any prior experience wearing a respirator, but to be able to participate in our study, we trained them on how to put it on and how to wear it and how to perform the test exercises. We did require that they were clean shaven on the day that they were fit test. And when we did the fit test, we used assisted donning. So we helped them get the respirator on so that we could achieve the either the pass or the fail fit that we were looking for. So the test fails is what was kind of a challenge for us. So there had been another fit test study, like an evaluation of a new method using the port account instrument recently. I think it was published in 2014. The way that they achieved the fails is they just missized the respirator, which makes sense. So we attempted to get fails through missizing, but because the QuantiFit is so sensitive and it measures leak directly, anytime we tried to missize the respirator, the QuantiFit would abort the test, and it was basically a catastrophic fail. Because with the QuantiFit, if it measures a leak greater than 1,530 liters per minute, then it won't complete the test. And so because we couldn't achieve fails through missizing, instead we chose to use artificial leak paths in order to get those fail tests. We used 3 different half mask respirator brands. So this was our variety. We used the 3M half mask and the Draeger half mask that's shown here. Those all came in 3 different sizes, small, medium, and large. And then we used the Dentec half mask respirator that came in 2 sizes, a small, medium, and a medium large. And so overall, we had 8 different respirators. And the 3 masks were used pretty much evenly in the study. And if you have any questions while I'm talking, it doesn't bother me. If you want to interrupt and ask, feel free. So the way that we measured the fit factor is we had the subject put on the respirator, and then they had to wear it for 5 minutes, the acclimatization period. This is actually a requirement by OSHA when you're doing a fit test, is that you put the respirator on and wear it for 5 minutes before you start the test. And then we did the exercise for both methods in succession during the same respirator donning. Now, ANSI does specify that they want you to alternate which test you do first so that you don't introduce like a test order bias. However, because the redon method involves taking off the mask, that wouldn't exactly be in the same respirator donning. So we chose to do the reference method first every time, followed by the redon. And I called it the fast redon, the modified redon version of the test that we were evaluating. So we performed both of those exercises in succession, and then we had our QuantiFit connected to the computer, and we used OHD's FitTrack Gold software in order to execute the scripts of the test exercises and calculate our fit factors and record our data. And then that data was exported to Excel to do the statistics that are required by ANSI that I'll show you in just a second. So this test actually involved two parts according to the ANSI methodology. So the first thing that's required is you have to determine what they call an exclusion zone. So the exclusion zone is basically the range of the fit factors that are going to bracket that pass-fail criteria. So in our study, we looked at half-mass respirators. So the pass-fail criteria is 100, a fit factor of 100. And so what we needed to do was define the fit factors that bracket 100 that we would consider unreliable just because of the variability of the method, the variability of the instrument. And so ANSI says that they recommend that if for the reference method, so this is our 8-step method, any fit factor that's within one coefficient of variation of the required fit factor should be excluded. And they don't mandate how you do that, but they make a suggestion that you do repeated measurements on the same subject that has an overall fit factor near the pass-fail requirement. So that's essentially what we did. We had a subject that had a single subject with a fit factor near 100, and we did repeated measurements on that subject to determine the coefficient of variation of the method. So that was part one. Then part two was the actual comparison of those two methods. So we did the sequential fit test. We did the reference method first, followed by the modified read-on method. To meet the ANSI requirement, just as a reminder, we have to have at least 100 fit test pairs, at least 25 participants, and then 50 of those fit test pairs have to have failed the reference method. And this is a fail outside of that exclusion zone. So ANSI says that if the new method is going to be viable, it at least has to have a test sensitivity equal to or greater than 0.95. So essentially what that's saying, the test sensitivity, is that you have to have a 95% probability that the new test will correctly identify a fail. And so if the reference method fails the fit test, the new method also should fail the fit test with a 95% probability. So that the sensitivity is really the only requirement for the ANSI standard, but they also recommend that you calculate these other statistics as well. So the other things that we calculated were the specificity of the method. And so the specificity is just the probability that the new test or modified read-on method could correctly identify a pass. ANSI doesn't have as high of a recommended criteria for specificity. They just want at least greater than 0.5 or 50%. And then these other ones, the predictive value of the pass and the predictive value of the fail, that's just kind of looking at it in the opposite order. So the probability of passing the reference method when the new method passed, and the probability of failing the reference method when the new method failed. And then they recommend you calculate a kappa statistic, which is really just the degree of agreement between those two tests. All right, so these are our preliminary results. The exclusion zone determination is complete. Can I?
Yeah, if you slide over, you should be able to.
Let's let Brenda in.
Yeah. Come on, Brenda.
Okay, there we go. All right, so the exclusion zone determination, this phase of the study is completed. And so essentially what we did is we took the same subject that had a fit factor near 100 and we did sequential tests. So we would have the subject don the respirator and we did 5 sequential tests during the same donning using the reference method. We actually did 4 trials of this. And so for each trial, we calculated the mean and the standard deviation. And then we calculated the overall combined mean and combined standard deviation. And the coefficient of variation from those trials was 0.19. So that corresponds to an exclusion zone between 81 and 119. So essentially what we're saying is that if the fit factor fell from anywhere from 81 to 119, we considered that an unreliable measurement of fit just because of the variability of the method. So this is not comparing apples to apples because the QuantiFit is a controlled negative pressure instrument and the PortaCount is an ambient aerosol instrument. But it's worth noting that in the previous studies with the PortaCount instrument, they found a exclusion zone, Richardson, that had the study published in 2014. Their exclusion zone was 82 to 123. McKay and Bradley, in a study before that, showed an exclusion zone between 94 and 106. So it is interesting and worth noting that the exclusion zone we found in our study was very similar to the exclusion zone for ambient aerosol methods. My buttons stopped working. So I think I've lost my cursor. There we go. 2 screens is hard to navigate. All right, so here are our preliminary results for comparison of the fast read-on method with the reference method. So far we have 22 participants, 16 of those were female. So we got 3 more people we got to get between now and Thursday because my students who helped me on this have got to present a poster to AIHCE. It's due Thursday, so we're going to get it done before then. We've got 22 participants and we so far have had 123 pair fit tests. 50 of those had a reference fit factor less than 100 and 73 had a reference fit factor greater than or equal to 100. And this shows the distribution of those fit factors. And so a requirement, the ANSI standard is that you have to bracket the pass-fail criteria with all of your tests. So you can see that we do. These data points shown in red are the reference method fit factors that fell within the exclusion zone. And so these 10 paired fit tests were eliminated from our statistical analysis to calculate all those criteria recommended by ANSI. Another requirement of the ANSI standard is on your failed fit test. You can't have all of those bunched up towards the lower end of the range. They want those failed fit tests to kind of be evenly distributed. So this histogram here just shows the frequency of our failed fit test. And so you can see that they're reasonably distributed below 100. Okay, so this is our graphical representation of all of our fit test pairs. So you can see the fit tests that fell within the exclusion zone, they have been omitted. We have 113 fit test pairs here. And you can see that we've got pretty good agreement between those. Most of those will fall on that or near that linear regression line. You can see, so the ones where you have, I think my pointer just stopped working. Oh, there it is. So here we have where we failed the reference method and we failed the new method. And then the ones over here are where we failed or where we passed the reference method and we also passed the new method. So that's where we want our data to lie if we've got a good viable fit test. There was only one instance where the test actually failed the reference method, but the new method passed it, and that's what we don't want. And the fit factors for that, if I remember correctly, oh, we got somebody else we need to admit. Multitasking, we can multitask, we're good. If I remember correctly, and I've got it over here, but it's cutting off my screen. No, I don't have it. I've got it on the next slide. I'll tell you what these values were in just a second. But
Alex, don't let him in.
don't let Alex in. You didn't tell me I was going to have to be doing all this multitasking stuff.
You know, I'm silly of me. I thought people might be on time.
On time, it's okay.
Within an hour.
Let's look at this data in our 2x2 table here. So yeah, here is our data in our 2x2 table. And so you can see that the majority of them were in, good agreement. The one that, we really pay attention to is the sensitivity, because what you don't want with a new fit test method is a new fit test method that's going to pass someone it should have failed. And so we only had one incident of that. And in this situation, did it pop somebody else up? Okay, in this situation, sorry guys, you gotta be on time. The fit factor for the reference method was 77. So it failed them with a 77. The fit factor for the new method was 123. So they were really, really close. So here are our actual statistics. And so far with our data, we have a test sensitivity of 0.98. So that means there's a 98% probability that this new modified read-on method would correctly identify a fail, which is what we want. The other thing that's worth pointing out, even though these are not a requirement of the ANSI standard, they're still good to report. And what I really like is also this test specificity. So this is the ability of the new method to correctly identify a pass. Now, ANSI only says that they want to see at least greater than 50%. However, from a practical standpoint, you don't want your new method to fail someone that should have passed, because that just means you're going to have to do repeated fit tests, and it's going to take you more time on something that's not necessary. So this test, this new modified read-on method, is also got a test specificity of 0.97. So there's a 95% probability it will correctly identify a pass as well. So I think that's very good. And our data shows that we've got really good agreement with a kappa statistic of 0.94. All right, so preliminary conclusions, unless we just have a big flub in the next 2 weeks. I may be jinxing myself since we're not. I know. Why did I speak that into existence? I don't think they will. So this fast read-on method would reduce the duration, if you're looking at the reference method, from 9 minutes to 2 minutes. That's a lot of time when you've got to do multiple fit tests. If you're doing the read-on method, you're still going from 3 minutes to 2 minutes. So you shave off a minute per fit test, you're saving a lot of time. With a test sensitivity of 0.98, it's viable. So it's got the potential to benefit industry quite a bit. So our next steps, like I told you, we've got some more fit tests we're going to complete before we submit our poster on Thursday, and then we'll redo the data analysis. And then we're going to also evaluate what I like to call the super fast read-on, because super fast is really fun to say. So the super fast read-on, we're going to go back and recalculate the harmonic mean of those fit tests and leave off that last read on and see, would we still have a viable fit test if we left off one read on? And so we just had the 3 static positions and 1 read-oning of the respirator. If that proves viable, it would reduce the amount of time required to do a fit test to 1.2 minutes. So that would be a huge benefit to those that have to do multiple fit tests in the year. So 2 students helps me with this research, 2 undergraduate students at UNA. Their names are Riley Duncan and Olivia Dawson. They have done substantial work and been instrumental in getting all of these fit tests completed. I wish they could be here with us today, but they are actually at a chemical plant in Muscle Shoals doing some air sampling. So they are learning how to apply what they've learned in class in the field. So they had to be there at 5 o'clock this morning. I told them, suck it up, Buttercup, it's part of the job. But they've done a great job. And then I also like to thank OHD for their partnership in this study. And then, of course, NIOSH, UNA are the recipient of a training project grant. So this study was funded partially through that grant through NIOSH. We're very grateful for their continued support. So with that, does anyone have any questions? Yes, ma'am.
Ms. Shawn, thank you so much. That was so good.
Thank you.
So I knew Ms. Shawn when she was a little person.
Yeah.
She's always been.
I've always been a little person, but she knew me when I was a baby graduate student. She was on my dissertation committee.
That was wonderful. Thank you so much.
Yes.
So the students, they obviously were very engaged in the process.
Yes.
So did you have to use an incentive to get the subjects like
We did use incentives. So if we recruited people for the study and we asked them to do 6 fit tests for us, 6 paired fit tests for us. And so the incentive, if they completed that, was a $50 gift card to Target. And then if they didn't complete all of them, we kind of subsidized that incentive with a coffee mug and a t-shirt, depending on how many fit tests that you completed. But our study was approved by the IRB, and so they approved those incentives.
And you get them
Yes.
just from the campus?
Just from the campus, we posted flyers around the campus and we had people sign up. So, yeah.
Thank you, Ms. Shawn.
Yes. Yes, ma'am.
Question. So for the participant you choose for your study, how did you determine that if they are medically qualified to be arrested?
We didn't do PFTs, but we did have them complete a medical questionnaire. And then we had them, if we gave them some instructions and said, if you feel like that you're uncomfortable during the fit test, there was a hand signal. They had to put their hands on the top of their head and we terminated the test. However, we didn't have anybody who needed to terminate. Yeah, but we did a medical questionnaire. Yes. Hey, Jake.
Great presentation. But I just have like a quick question about your recruitment, just kind of knowing the general mindset of the student body at UNA. I was wondering if you thought that the reason you kind of had a disproportionate amount of female to male recruits was because of the clean shave stipulation?
I don't know. I honestly haven't thought about that. Possibly. I do know I was looking at the distribution by males and females, and I looked back at the study that was done by Richardson, and he actually had more males than females. So possibly, maybe, I'm not sure.
Well, it's interesting that it doesn't seem to play that big of a factor
Yeah.
compared to the other literature.
Yeah, we have more females on campus.
Well, yeah, I
So,
believe that. Yeah.
So that may have been it.
Yeah.
Yeah, hard to tell. Yes.
So how did you determine the amount of time to increase like previously we had the other sectors, you like
Well, the reasoning behind it is it's a 30-second, just breathe normally. And then we take the measurement when they're in that static position. So if they're face forward and then they bend down and then they do like a head shake and face forward. So eliminating just that 30 seconds, just eliminating the exercise, keep the static position.
Can I actually speak to that?
Yeah, and yeah, Stephanie can probably speak more to it.
What we found is that our users are already doing that. So what we're really trying to do is bring our users into compliance, because they're not standing there for 30 seconds and then engaging the test. They're engaging the test. So we're hoping that this will show that they're already in compliance, and then they'll just be in compliance. Would be the ultimate goal.
That's true. And speaking from when I used to work in industry as a practitioner, I mean, we did it. We didn't do the 30-second exercise. We just said, okay, hold your face forward, hold your breath. Okay, bend over, hold your breath. So
So I think the education for both of you are so good. Our purpose is to be a TSI, basically, to shorten the time.
Well, not really. They now have their FastFit protocols. I don't know that it would be a huge selling point. I know it was when their test was, 9 minutes and ours was less than 3, but going for 2.5 to 2, I don't know how big of a selling point that would be. For us, we started this we wanted to do this before those FastFit protocols ever came out. And it was with the motivation that we already saw that a lot of our users are firefighters, specialized police forces, they're not doing it. But if it helps, that'd be great. TSI, yeah.
TSI changes, this is your.
Right. TSI absolutely did that to people, to compete with us. But for the record, they're our biggest competitor. We are by no means their biggest competitor. So.
What's the difference in cost of the units?
You feel like I should know that.
I know the TSI is like 16,000.
So ours is like 9,000. But our biggest limitation is that we cannot fit the filtering face piece respirators. So that is,
So are you guys planning on
we've been planning on it. Yep, any day now. We're gonna have it out. COVID's really given us a push, so we'll get it done. LaShawn's probably gonna help us.
I would love to help you. Respirator fit testing, this type of research, because UNA is an undergraduate institution and our professors have, 12 teaching loads, and our students who sign up for research hours are also, taking 15 to 18 credit hours. So this type of research really lends itself to our institution. It's something the students can do. They can fit test on weekends and.
You'll be glad to know that the TSIs have gone up in price.
Yeah, when Molly said 16,000, I was thinking, I don't feel like I paid that much when I bought
Like
one.
6-7 years ago, so.
Okay,
Well, TSI is not hurting for anything. They at certain points during the pandemic, they sold out, they were on back order, so.
does
Don't worry
anyone
about that.
online have any questions for me? And you want to put them in the chat or unmute yourself? Or can they unmute themselves?
I actually don't know, though. I think I put it in the chat. I didn't do.
You would think with
that?
teaching through a pandemic
Oh,
and having
poor
to do it, somebody we need to let someone in. You would think teaching through a pandemic and having to do in-class and virtual at the same time, I would have mastered this, but I have not, so. But thank you to our online participants.
Thanks, guys. We're all just doing the best we can with what we have. We're going to take a break here. So y'all take a break, move around, and we'll have our next speaker at, what's on the agenda? Y'all, it's a pretty long break here. Our next speaker isn't until 9:45. So take a break. I'll leave this powered up. Now you can say hello.
Hey Laura, hey Alex, hey everyone. We should ever get everybody to walk past. and
Yeah,
speak to
We'll get
everybody.
everyone to walk past and do a,
Like a
do an
socialization.
yes.
Oh,
Hey,
that was
Alex.
way.
We
Wish you were
appreciate,
here.
we do wish all of you were here, and we appreciate you being here virtually. Okay, I need more coffee.
Okay.
called Technical Environmental Services, where we do environmental, industrial hygiene and safety consulting services. I got to try to stay behind here. I have a tendency to walk around. So I have a master's of science in public health and industrial hygiene from Tulane University. My undergrad's in biology from Holy Cross College. I sit on the National American Industrial Hygiene Board, on the finance board. I have one more year there, and I hope to run for the national board, to be involved, continuously involved in the national section. I'm a certified industrial hygienist and a certified safety professional, and we're opening up an office here in Alabama. So I'm trying to come here and understand the industry around here and see who's who and what's what in Alabama. So enough of that boring stuff. Let me show you some fun things. Like, what do I like to do? Okay. So I threw a couple pictures up here of hobbies. This is a 1958 Chevy Nomad. My dad's recently retired. He needed a hobby, so I gave him one. And this is where we're at now. So she's almost done. This is all work, just my dad and myself. Of course, we had some other people helping with chrome and sandblasting and things like that. Interesting industrial hygiene fact, sandblasting this car and the metal started melting. So I was like, Dad, what is that? Well, it's actually lead on there. And I have some pictures of some of the doors where today we use Bondo. But back in the day, they would bang out the metal as much as they could and put lead in there and file that down. So I had a lot of lead exposure building this. Probably asbestos exposure underneath and somewhere on there too, I'm sure. A couple more pictures. I have 3 kids. We have a lot of hobbies. We hunt, we fish. This is my oldest and my youngest. This is my middle boy. He's doing environmental science. My other ones chose to do something else. He's at LSU, go Tigers. So silence? Yeah. I'm just kidding. Sorry, everybody on there. Yeah, but he's at LSU. My daughter's at LSU. My oldest is in construction. We go hunting every year. I love hunting. I love jet skiing, boat riding, sitting on the beach.
Oh, yeah.
Yeah, that's Orange Beach. Oh. Yeah. We love traveling. This was recent. Anyone know where that is? Amarillo, Texas, on the way from California. We drove from California back home to Louisiana. So we like traveling a good bit. All right. So that's a little bit about me, some legal jargon about this, intellectual property, all that stuff. Just please use this information, but if you're going to reuse my slide, just make sure I let you know. I mean, you let me know.
And I'll let you know.
Yeah. All right, let's jump into this. What are we going to talk about? I'm going to talk today about designing and evaluating temporary confined space ventilation systems. So how many of you guys have ever seen a temporary confined space ventilation system in practice? Any few? Okay, fantastic. All right, so this presentation was originally put together for some folks in industry. I've been in industry 20-something years, working for plants, chemical refinery type plants, and I see a lot of issues with people working in confined spaces. So they go, okay, well, I'm gonna go through ventilation on that. And the thought when we're theoretically designing it is fantastic, but in practice, it looks much different. So that's why I put this presentation together. So the purpose is just to provide some guidance and an opportunity for discussion on how to design and audit temporary confined space ventilation systems. This is put together so that we can, some confined spaces have existing health hazards in them. If you think about like these columns that you see in refineries, they flush them out the best they can with solvents and then maybe even with water, but there's still some level of contamination in them. Or I could be in the confined space. Maybe it's the perfect confined space, brand new, but they're welding in there, or they're having a blast in there. I'm introducing the hazard, right? Noise, things like that, even though we're not talking about noise today. So we got to design these to protect these folks. So here's my objectives today. I'm gonna start with some real basics on what is the definition of a confined space. Then I got to talk about a few definitions to get everybody on the same page. Then I'll tell you about my resources so everybody can reference those. Some common concerns and issues. Oops, why is that not showing up like that? Some common concerns and issues, and then I'll talk about the procedural things that we do in industry, where if you're doing an inspection in a confined space, perhaps you need this level of ventilation versus I'm going to be doing a lot of stainless steel welding using flux core or something like that. I need this level of protection now. So I'll tell you about our procedures. Then I'm going to show you, I got pictures all throughout here and some videos. I'll tell you about some auditing issues that I've seen out in the field. And then we'll talk about some training, some record keeping. And then I have an example of a real world design that somebody brought to my attention. Somebody brought to me and I designed it for them. So I'll tease your brain about that. So let's start with some basics. What is a confined space? Most of you guys know all this, right? Yeah, you laugh because you know what a confined space is, right? So you can bodily fit into a confined space. It's not designed for continuous occupancy, and there's limited means of egress, like a sports car or a porta potty. But that doesn't mean it's a permitted confined space. So you got to have a confined space. Now, a permitted confined space. What is that? That means that confined space now has the opportunity for entrapment, engulfment, or a hazardous atmosphere. Whether that exists in the confined space because of the nature of it, or you're making that hazard in the confined space. That makes it a permitted confined space. And when it's permitted, there should be a procedure at whatever facility you're working at that says, before I can enter into this permitted confined space, I have to do these things, which includes, more times than not, industrial ventilation, along with some industrial hygiene sniff tests, 5-gas meters. Maybe we're doing some traditional industrial hygiene sampling on them. So here's some examples of entrapment, maybe engulfment, and he's going in, or he or she's going in with some PPE, so there must be some hazardous atmosphere in there, or the potential for it. So let's talk about some definitions specifically around designing temporary confined space ventilation systems. So LEVs, local exhaust ventilation, I think most of you guys know what that is. That's an engineering control, right? It's mechanically removing the hazard from the worker's breathing zone. I know it's an engineering control. Okay, let me qualify this. I know it's an engineering control, but I believe it's a very bad engineering control. And here's the reason why. It needs a lot of training, continuous training. And I'll give you an example. I have several welders. Maybe they're making a linear weld and they start with an LEV, probably 6 to 10 inches away. Great, 100 feet per minute. But if they're not trained to drag that LEV with them as they're making that linear weld, guess what? It's not effective anymore. So engineering control is supposed to work without the human piece in it, right? For most engineering controls. This one is a little more challenging. A lot of training, continuous training needs to happen. So I have a cool little video. This is one of our operations. Let me lay this out for you. This is in a barge. There was an engine there. They removed the engine. That's motor mounts, carbon steel, and they're going to using an oxyacetylene torch. They're going to cut that. A lot of smoke generation. Carbon steel exposure. Really, we're worried about manganese in that. I see more times than not, I'll see manganese as the biggest issue. There's some other ones, lead. This one happens to be fully abated where they're cutting from the previous paint. But we still pop the action level with ventilation, abatement of the paint that contained lead. We abated it, we ventilated it, I did monitoring, and I still popped the action level for lead in this situation. Check this out. Uh-oh, we're stuck. So this is just a makeshift LEV system, is all that is. This is what happens in the real world, right? You got this tubing and it's going to some kind of air mover and it's under pulling negative pressure. And you can see them torch cutting it. I have another view of it. This is another view of it. They did a really good job of capturing the smoke. Obviously, they're not capturing everything. There's some level of exposure from those sparks and when they cool off. But we measured it. They were at least 100 feet per minute. And you see they got it like 2 of them, LEDs, right on where the generation of smoke's coming from. And then I had in the general atmosphere, this is within an engine compartment, I had a general ventilation going with about 4 air changes per hour, and I still popped the action level. Where's all that lead? It may have been in a contaminant in the steel. It may have been impregnated in the little micro holes within the steel. Don't know exactly. But I was very shocked because I tried to do everything per the book, right? Still shocked. And I had more than 4 air changes per hour. I had somewhere around that, probably 6 to 8 in reality, plus the LEV, and I still failed the action level. I still popped the action level. Very surprising. But before we put the ventilation in, I had to have them in a full face respirator before. So I made a pretty good significant reduction. So let's talk about some fans. There's axial fans out there. This is probably one of the more common ones you'll see in the industry. This is what was on the other end, this middle picture of what you just saw, that video. An axial fan. They're usually 18 to 30 inches. You'll hear the word Copus blowers out there. Copus is a manufacturer. It's probably the most common that I see out there. They're really good air movers. The other thing you'll see out there are these eductors, air horns. Everybody calls them air horns, right? They're not, and I've seen them used out there. They don't move as much air. They're not as effective as axial fans, but for certain situations, it's small spaces predominantly. We'll see this use out there. These are all pneumatic. There are some axial fans that are electric, but in general, they're all pneumatic, which is important when you're auditing. And I'll show you a picture later on, but when you're designing this, you'll design it for 80 PSI, so it moves this much air through that axial fan. Well, I have a picture later on, but you'll have a connection to an air supply. And you'll go audit it, you'll design it, you'll install it, you'll audit it, and it's perfect. But then what you fail to realize is that everybody's connecting as the turnaround goes around. So instead of 80 PSI, now all of a sudden you have 10 PSI and it's not effective anymore. That's why the audit piece is important. So let's talk about capture velocity. I think everybody in here should know what this is, but what we're trying to do is measure, well, this one. So if you're using an LEV system, you want to be around 100 feet per minute. That's what the literature says, right? So that's, if you're using, for most LEV systems, I find 6 to 12 inches is going to yield that, okay? 6 to 12 inches will give you 100 feet per minute at the point of generation. So everybody's like, yeah, we can do that, right? The problem is when you go tell a welder that you want to use an LEV, and I've had many, many of these discussions, and you start telling them what the LEV does, it pulls air. They're going to go, I can't use this. Well, why can't you use this? Because welding requires a shielding gas around it. And if you remove that shielding gas, it sputters, it goes, it looks terrible. It's a terrible weld. If you ever talk to a welder, they really want their shielding gas, and you can't mess with that. But the truth is, when you actually calculate 100 feet per minute into miles per hour, that equates to 1.13 miles per hour wind speed. Once you explain to them that I can blow harder than that, I'm not gonna, if I properly do it, I'm not gonna remove their shielding gas. Remember, training. Then they'll start to use the LEV systems. The other thing I find with LEV systems for welding, again, training. The proper way is to pull the contaminant away from the person, right? So if I'm welding in front of me, I'm going to pull it away from me. Well, that's in my way as a welder. So I'm going to put that thing right here. Well, now I'm pulling it right through my breathing zone. You know, or the best spot is to put it along if it's a flat, put it along the piece of metal. So I'm using it almost like a flange. Then my capture velocity goes out further. So there's a lot of practical things you got to train people on when you're talking about LED systems. Makeup air, super important, makeup air. So if we're pulling, when you guys have seen your ventilation systems in the field, are they pushing air or pulling air from the space? Pulling air, negative, right? Same here, pulling air. So if you're pulling air from a space, air's got to come back, the makeup air, right? So if you've ever taken a straw and stuck your finger at the bottom of the straw and tried to suck on a straw, what happens? It collapses. You can't pull air, right? So your limiting factor is not often the fan size, but it's your makeup air. And there's all sorts of auditing things that you have to do because people will put trucks, they'll put their welding machines right by the makeup air. So now you got all that CO going into there. Or they're doing some work around there. Maybe they're blasting. Maybe they're mixing gunite right next to the makeup air. Gunite has silica in it. You got some potential, some gunites do. So makeup air, super important to make sure you have clean makeup air going into your confined space when you're ventilating it. So these are just some instruments that I hope most of you are familiar with. Anemometers and velometers, they measure wind speed in feet per minute, and you can calculate that into CFM. So when I measure my confined space effectiveness in the field, I measure at the makeup air. Because most of the time I'm seeing negative pressure in a confined space. So I'm going to the makeup air at the opposite end, the furthest away from my air mover that I could find, and I'm going to measure there. Because then I account for all the restrictions within that confined space, okay? So you'll also find, and I have a short little video here trying to show this, you'll also find that the air is extremely turbulent and hard to get a true reading on the positive pressure side. So if you watch my anemometer here, it's got a pretty good delta in the order of, maybe 80 feet per minute. So what number do I pick when I'm doing the positive pressure? So when you're trying to figure out the effectiveness of it, again, I go to the makeup air side, and you'll see that the air it's more smooth, if you will. You see, it doesn't jump around as much. Just trying to show a simple video of laminar versus turbulent air. So the other important definition when you're designing, you'll pick a fan, and that fan will say, hey, I can move 20,000 CFM. Free air volume, which is a lot of air. Free air volume. Free air volume means that that's the best that machine's ever going to do, regardless of all the restrictions and stuff going on. So that's the best it can do. So when you're designing, we typically design what I call guerrilla engineering. If I need, 10,000 CFM, I'm going to pick a fan that'll give me 20,000 CFM, because I know darn well once all the things happen in there, I'm going to probably be at my target rate. So free air volume is important to understand when you're looking at these instruments. So here's some common issues that we see out there. I mentioned the first one. Bringing the contaminant across the person's breathing zone. So sometimes it's unavoidable. But if it's one person in there, you could probably design it, maybe design it so it doesn't go across their breathing zone. But the truth is, in the field, you're limited by whatever holes, manways are available to you. And they move all in that confined space. So at some point, it's probably going to go across our breathing zone. But it's something we want to look at. The exhaust, where the air is coming out of the confined space, let's not blow it right on people. Let's try to make it go away from them. I can't tell you how many times I've seen that. And there's choices. You could even put, we've had to even put bagged socks, if you will, on the exhaust. So it cuts down the amount of dust that we've had. So there's some solutions if it has to blow in that way. Of course, electrical grounding, and make sure your energy sources are secured. It speaks to, I'm specifically talking about the pneumatic sources. So you'll see in the field during these big turnarounds, you'll see one big main airline coming in, and then you'll have 10 options to hook up. And people come and hook their breathing air up. I mean, we need breathing air, not breathing air, we need air to run pneumatic tools and whatnot. Well, the problem is if you only have so much PSI going to there and you need 80 of it, you got to make sure those other pieces are locked out or they're going to use it. If it's available, they will use it. They being the folks in the field. And remember that, and make sure the air movers stay on the whole time. Oftentimes when you get a permit for a confined space, they'll only go sniff that confined space sometimes at the beginning of the day with the air movers on. So if that air mover turns off for one reason or another, it should void that permit because now the concentrations of the gases in there could be higher. So those things got to remain on at all times. And often what I find here is that they don't have enough pneumatic air. So we don't need this confined space thing. We're not in that confined space right now. So let's turn that one off and use this air over here. The problem is they don't cancel that permit. So then the next person goes in thinking that they're good to go. That's a problem that I see in the field. Short circuiting. This is one I see pretty often in the field. They'll take those air movers and they'll put it like that picture up there, where it's half on the manway. Well, now I got short circuiting happening. I'm not pulling air from the confined space. I'm pulling it from the shortest route, the least resistance, which is around the corner, like you see in the top one. So they designed these Copus blowers and these different instruments to fit these manways. Or they have, I've seen plywood, just put plywood on there to prevent that short circuiting. Okay. All right. This is one where it says, especially for the South, when it's hot air rises, right? So let's not fight that natural tendency of hot air to rise. Put your air movers towards the top of the confined space when possible. Just to not fight that natural tendency of the hot air and buoyancy to rise. Put it towards the top. The truth is it's hard sometimes because you're limited by the amount of manways available to you. Let's see. Oh, this is about makeup air. So this picture over here is showing where you got this, the picture on the left is showing where there's a dead space right here because I put my fan at the bottom in my makeup air and I got this little guy going up here. So you can resolve that by just using some ducting, bring it up to the top. Now I'm sucking the air from the hole. I'm ventilating the entire space. I don't see that one as much. So that's some common issues. Let me talk to you about the procedure. So you can go through all sorts of standards, and I'm told that there's an ASTM standard out there that actually references this 10 air changes per hour. I haven't found it, but I'm told. So you can go through all throughout OSHA. OSHA doesn't tell you how many air changes per hour you need in a confined space. The only reference I can find in OSHA is about asbestos, and it says 4 air changes per hour in a containment. But in industry, what I've seen out there is 10 air changes per hour is sufficient for doing like inspection type work. If I gotta go in there and inspect, which usually happens on the front end of a turnaround, right? I shut it down, I open it all up safely, I put my controls in place, now I gotta go in and make sure that this pipe is not all corroded, for instance. Inspection, 10 air changes per hour. But if you're actively doing work in there, welding, refractory work, those are the two most common ones I see out there. You want 2,000 cubic feet per minute per person making a mess in there. So let's say I got 3 welders in there. I need 6,000 CFM per welder. I mean, total in that confined space. So you have 10 air changes per hour is the common practice for just going in and doing inspections. But if you're actively working in there, you need 2,000 CFM per person actively generating the hazard. So you might have a pipe fitter in there and a welder, for instance. I don't necessarily need 4,000 CFM because a pipe fitter by nature doesn't need, that person's holding the pipe together, maybe a tack here and there. The welder's making the mess. But let's say that I'm blowing in or busting out refractory within there, and I got 4 or 5 people busting out refractory. That's 8,000 CFM that I need in there to make sure that they should be good to go. And I say should be for a reason. So I covered this a little bit. Your LEVs should be about 6 to 12 inches away, but you got to go measure that and train people. And I have a short video on this in here. And again, 100 feet per minute is about 1.13 miles per hour wind speed. In my experience is when I explain to especially for hex chrome, early on, hex chrome, and manganese is an issue too for carbon steel. If you're doing anything but TIG welding, if you flux core, if your person's flux core welding or stick welding, MIG welding, certainly torch cutting on carbon steel, there is a manganese issue there if they're doing it for any appreciable amount of time when you compare it to the TLV. Here's the problem. OSHA has a 5 milligram per cubic meter sealing limit, sealing being instantaneous. I don't know how to measure manganese instantaneously. So I use the TLV, which is 0.02. And there's some research out there. Manganese causes Parkinson's like disease. Okay, and there's a lot of welders with that disease. And now if my hand shakes, guess what? As a welder, I can't weld anymore. So a lot of people, about 5, maybe 10 years ago, I saw industry really starting to talk about manganese. And they put everybody in a half-face respirator, which is a good move for most situations. But now we've been able to effectively train people on LEDs, and we've gotten them out of respiratory protection for hexavalent chromium for stainless, also for manganese for carbon steel. And that's the selling point to a lot of the welders. A lot of people don't want to wear that, especially when you're trying to keep that welding hood up and down. There's PAPRs and things like that, powered air purifiers, which are pretty cool. If you ever worn a powered air purifier, especially with the one up here, that's heavy for a while. I weld and I wear something like that. That's heavy on the neck. Okay, well, I got this one right here. Well, that's cumbersome. There's a lot of tubes still going up if the filter's at your waist. They don't want to wear any respiratory protection. So that's where the LED comes in. That's my sales pitch to them when I'm trying to sell it to welders. I potentially can get them out of respiratory protection. So here's a little video that I took from that source up there. It shows capture velocity pretty well. Let's see if I can get it to play.
Ideally, we should determine the capture zone with the process running. In this demonstration, we're using smoke to represent the contaminant generated by the process. Begin by moving the smoke source around the hood inlet, gradually moving further away from the opening until the full extent of the capture zone can be observed. The position where the smoke is no longer being drawn into the hood is the boundary of the capture zone for this process. For this demonstration, a yellow wire loop is fixed to the hood to represent the shape of the capture zone for this process, An anemometer is used to measure air velocity at the edge of the capture zone. In this example, the velocity at the edge is around 0.2 meters per second, and this is known as the capture velocity for the
That's about
process.
60 feet
The
per minute, I
velocity
believe.
at the face of the hood is 3.5 meters per second.
That's about
Typically,
90.
at a distance of 1 hood diameter, the air velocity will be about 1/10 of the velocity at the face of the hood. The capture hood is marked with the effective capture distance for this process. This is almost always smaller than the user expects, and it's due to the fact that the air
So what I found in the field, they use, if, to at least for teaching, they'll use a broomstick. They'll use anything available, right? They use a broomstick, and they're telling them about 6 to no more than 12 inches. It's usually 6 to 8 inches is what they'll put that broomstick. So that way it's a visual reminder of the welder to keep that thing moving as they're moving. Oops. So this is why I said some situations require both general dilution and LEV. Remember I showed you that other, that lead one I told you about, and I had general going, you can, go ahead, I'm sorry.
No, well, we had a question.
Oh, yeah, yeah.
Brenda.
What's the question? Oh,
So I have a question. How are you addressing inside of confined space all your mixture effects of your chemicals? Are you doing that calculation instead of just focusing on like manganese or lead? Are you looking at the totality of the mixture of the metals?
yeah, so this particular presentation is about setting it up so that we can at least design a temporary confined space ventilation system. You'll see in here, this slide in particular says that it may need a combination, and you got to go do your industrial hygiene sampling just to make sure that what you're designing is effective. So for us, most of our clients want to see them individually. So we don't do the synergistic effects for at least welding fumes is what you brought up. I have done that in the past for them, or the additive effects. But most of our clients, they still have issues complying with manganese. So when you try to tell them about the additive effects, it kind of blows their mind a little bit. So what I'm trying to do is get them compliant with manganese, which will help with all the additive effects too. And maybe we can progress to that point. Good question. Does that answer your question?
Yes, thank you very much.
Yeah. So to this point on this slide, remember I showed you that ship. We were in the engine room. I had general going with about 8 air changes per hour is the best I could get in there with LEVs, and they were putting LEVs right on the smoke generation. And we abated the paint off the carbon steel. And with air monitoring, we still found that there was a lead issue, which was mind blowing to me. So to your point, we got to do some air monitoring just to make sure what we're designing is theoretical and it's still sufficient to protect people. So here's an example where we did, this was a designed ventilation in the front part of a ship. That's the front part of a ship flipped over, okay? And it's real awkward in there. There's actually 3 compartments in there. So we designed originally, let's see, they had 2 blasters in there, blasting carbon steel. It wasn't painted, so no lead, but they had to use sand. So sand equals respirable crystalline silica issues, okay? For whatever reason, they couldn't use a substitute for sand. So we originally had, there was 2 people, but we still had 6,000 CFM of air coming, it was negative pressure coming out of the confined spaces. There was 2 compartments, they were working in 2 of the 3 compartments. So the 3rd one was in another compartment, but they all kind of mixed together through small manways, small enough where you can get through, but small. They did have, there was no design for makeup air, no design positions for the air blowers to exhaust. They were actually exhausting down, which if you saw that video, is full of sand down there. So it actually created some sand issues within the building, some silica issues within the building. They did use a suppressant. They had some geoscreens up within the building to prevent the regulated area from extending. And they had a water truck wetting down the ground outside, okay? Outside this building. So this is an upside down ship inside of a building. This was the results for an 8-hour work shift. So pretty doggone high. The action level is 30 micrograms per cubic meter. I'm sorry, 25 and 50. I'm getting my constituents mixed up. Thought I was in lead. So that's significantly high. They were using, of course, blasting hoods, which they had from the manufacturer. I think the protection factor the manufacturer said was 10,000 on the protection factor. I think by NIOSH or OSHA, it's 1,000 without that manufacturing statement. So nonetheless, that's some high issues. All right, so the next go round, they had 2 in there. We bumped it up to 20,000 CFM on a dust collector. The dust collector was positioned outside the building, and then they had tubes coming into the confined spaces. We blew some air as makeup. We verified we had 800 roughly CFM makeup air going into the confined space mechanically. So we're doing a push-pull type system now. We sealed off some large openings with poly within the confined spaces to try to make the space a little smaller so we could pull air harder on it. And of course, some of the other things still applied where they had the geoscreens, the blast hoods, water truck, and all that. So the big difference was we bumped it up to 20,000 CFM on a dust collection system, and we're mechanically pushing air in. And we positioned them on opposite sides so that I didn't have contamination going through a breathing zone, okay? So this is where I got. So pretty good reduction. But still, that's some high numbers. If you ever fool around with silica, that's some high numbers. And we reduced the regulated area from 140 feet outside the building to 25. And that's that I know it's because of the dust collection system. So pretty good reduction. You know, short of this, and I've done this particular project a few times, and it varies depending on what's going on in the body positioning. If I'm blasting above my head versus below my feet, that's 2 different exposure profiles. It varies, but we've been able to make a significant reduction. The only way that they can make more is if they get rid of sand and go to like a Black Beauty garnet or something like that, or a wet blasting method, which they currently have chose not to. So let's talk about some auditing. Some field audits of temporary confined space ventilation systems, absolutely necessary. You could be the best designer in the world and it will be circumvented in the field. Absolutely gonna happen. So you gotta go out and audit it. My suggestion is, of course, when you install it or have it installed, you go audit it. But then you better go out there frequently throughout the turnaround. It's usually during turnarounds and shutdowns, and audit it, because it's a dynamic environment if you've ever been part of a turnaround. They run 24/7. There's hundreds of people there, and they circumvent, not knowingly, but they knowingly sometimes, they circumvent controls. Okay, so you got to audit frequently. This is that tree I was telling you about where we started out at 80 PSI. We did not lock out the different connections. And when I came back in 13 hours to audit it again, it looked like that. And now instead of 80 PSI, it was 15. And we ended up having to remove people from the confined space, fix all this. We canceled the permit. We fixed all this and put them back in the confined space after we fixed the ventilation and redid the 5-gas test. So auditing is super important. You know, if you're going to do a lot of industrial hygienists and engineers, this is how they get assigned designing confined space ventilation. They go, okay, you're an IH, you're an engineer, here you go, design this for me. And you're like, man, I don't know what I'm doing here, right? And there's some books you can read. AIHA and Mike Harris put out a real good manual around temporary confined space ventilation, which I've used as a resource here. So there's some books you can read, but if you can find a knowledgeable person to train you, that's what is ideal. My suggestion, I've seen this too. A lot of plants went through the trouble of designing temporary confined space ventilation systems 20 years ago and haven't updated them since. So, and I don't know that they're field verifying them. So if they work, they work. But if you're not field verifying, I don't know how you know it's working on each turnaround. But also when you design these, keep them as part of your record keeping, because it can help your company down the road prove a negative. You know, for if you got your industrial hygiene sampling and your company's getting sued, litigious reasons, you got your industrial hygiene sampling, you got your ventilation, that's going to go a long ways in court. Versus if you don't have that, your expert witness is going to have to say, hey, the industry practice is this, and maybe get some objective historical data from somewhere else and prove that that's accurate for your particular situation. That's a much harder hurdle than if you have your own. Much harder hurdle. Record keeping. All right, some quick fact check. All right, I think I asked this earlier. How many of you have seen a confined space ventilated through general dilution, where they got a fan on a manway and it's pulling air out? Okay, so that's half of this crowd. I can't see everybody on here. It's usually a third of the crowd. So have you seen it pulling air out, negative, pushing air in? And I asked this earlier, most of you said pulling, I think all of you, pulling air out, right? Anyone ever see forcing air in? Yeah, so I'll see it in maritime and telecommunication. That's the only two spots I've ever really seen it. Here's the thing, this is a bit OSHA verbiage. Let's fact check this. From OSHA, they require continuous forced air ventilation. That's your standard. So I scratched my head, I went, what is forced air? If I'm pulling air, is that forcing air through the makeup? I'm not sure. So I got OSHA actually in one of these talks, and I'll tell you what they said, but here's the answer. Forced air means positive pressure. By definition, that's OSHA's language. So everybody who's doing negative air is actually in violation of OSHA. I didn't know that. Oh, mind blowing. Because I'd say 90%, 95, 99% of what I see is negative pressure. That's not complying with OSHA. So I actually had OSHA in here from Region 6 in one of these talks, and they said, now he's not representing all of OSHA, mind you, but he said, look, man, you guys are ventilating it and you're doing a good job of ventilating it. Your industrial hygiene sampling supports that there's no additive effects, that there's no manganese issues. We're not going down that road with you. Now that's one OSHA guy, actually two OSHA guys. All right, so, but the truth is, they say forced ventilation. So I've done some negative air, I've done a lot of negative, but I've done some positive. They both have their issues. Positive pressure is actually it's gonna be more effective, but it's gonna cause a lot of turbulence going on in that confined space. But if you are right next to the confined space ventilator and it's positive pressure, you're gonna have fantastic air movement. It's when it gets down the road a little bit in that confined space where you have some issues. So negative and positive, it's a toss up. There's issues both ways. But the law says positive pressure. Who would have thought? Been doing this 20 years and somebody pointed that out to me 5 years ago.
Is that net positive pressure?
So it's going to be, you have to field audit that. Are you talking about the true effectiveness of it? Yeah, absolutely. Remember, you need 6,000 CFM 2,000 CFM per active worker in there. So you got to design your ventilator where you're getting that per person in there. And I guess you're measuring that on the intake side, because if you go try to measure that on the positive pressure side for one of these big air movers, I mean, it goes all over the place. And you need an anemometer that there's a limit. There's 2 anemometer type. There's your anemometer, you got to make sure does more than 5,000 feet per minute to do this work, because a lot of them peg out at that, and you'll have over that if you're auditing. So let's do an example. This is a real world one, by the way. So you're responsible. Now I've knighted you. You're responsible to go design a temporary confined space ventilation system. This is what you'll get. You're like, whoa, what the heck is that, right? This is a real world example of what I got. And I'm like, man, where's the vessel on there? I'm looking all over for it. Okay, but there's a lot of things going on there, and you got to decipher it. So what do you do? Step 1, information gathering. What can I get from that drawing? That's the first thing. I could probably get my diameter, length, manway locations, and my manway diameter. And in fact, you can. I'll show you later. Now you need to know, okay, what the heck are you doing in there? You just going in and inspect? You doing refractory work? If you're doing that, welding, how many people are making a mess in that? You need to know what's going on in that turnaround. So scope of work. If they're welding, what kind of metal are we talking about? We might be talking about some exotic, chromium containing that has a lot of chromium in it. How many people will be actively creating the hazard? Where will they be working? Now, that's a hard one. They can't ever answer that. Well, very seldom they can answer that, because they go in right here, and today they're working here, tomorrow they're working here, next day they're working there. They're all over this place, all over the confined space. That's a hard one. How many manways are open? Which ones are open? Which ones are going to be used for egress? So this is that drawing. I flipped it over and showed you where you can find the information, but the height is 212 feet in height, diameter is 96 inches. So you convert that, you end up with roughly 11,000 cubic feet of volume in that confined space. But it also shows you where manways exist. I'll show you that in a second. Oh, so where do you get all this information on the scope of work? It's usually a turnaround planner or an engineer of some sort. So let's say I sent them all my questions about, what are you guys doing in here? What kind of metal is this? So that person got me back that information, and he said, we're going to be removing and replacing refractory. And we're going to be welding a nozzle inside the confined space. All right, cool. What kind of metal? Oh, it's stainless steel. Okay, IH, hexavalent chromium, I got to think about. All right, and they're going to be doing TIG welding. All right, I've done a lot of welding. TIG's not that bad. It's pretty clean, but I still got to think about it. How many employees will be creating a mess in there? All right, I'm going to have 3 refractory workers and 1 welder with 1 fitter. So now I'm thinking, all right, I'm just going to design for these 3 cats. So now I need 2,000 CFM for those 3 refractory workers. So I need 6,000 CFM. That's how my mind thinks. I'm not going to design 2 systems. I'm going to go worst case scenario. Where will they be working? Wow. Refractory workers are going to work throughout the vessel. And the welder's going to be at the top. All right, cool. How many manways are open? All right, I'm going to open up M1, M3, M4, and M5, but M2 is not going to be open. All right, let me look at my drawing in a minute. All right, which ones are going to be used for egress? I don't know. You tell me. That's the answer's going to be, right? We're going to have to figure that out. But you can use any of these. So here's from my drawing again, there's my manways. And on the right side of the slide, it tells you the diameter of the manways. So you'll see M1 at the bottom, it's 24 inches. Actually, all of them through M5 are 24 inches, 2 feet. See the M2 is on the other side. That's probably why they're not opening it. They don't want to build scaffold up to it. There's nothing there. They're probably not going to build any scaffold there. That's my thought process. All right, and it's off the slide a bit, but you can see the top, there's on the left side of the vessel is M1 at the very top. It's cut off on our slide. All right, so now I know my manway sizes and I know where they're located. All right. So I know I'm going to design for 6,000 CFM for those 3 refractory workers, right? 2,000 CFM per person making a mess. I'm gonna probably use one of these axial fans because they're the most common out there and they're pretty good. And they make swing gates for them. Remember I told you earlier about short circuiting? They make man gates for it, but what's cool, manway holes, what's cool about this too is it's used for emergency egress. So if the stuff hits the fan in there and that's the hole I need to go out, I can use it. I can push that thing out of the way and get out. So those are cool as opposed to plywood. All right, so now I pull out the Copus blower manual and I got to figure out what these free air volumes are. So this is a list of, well, this one shows the diameter size first. So you'll see what I have highlighted is for an RF20 and an RF24 inch. In the RF20, you'll see we're gonna look at B, is 24 inches. Remember my manway is 24 inches, so that 20 is probably gonna work, but look at that RF24, that's too big, it's 31.2 inches. That's not gonna work, it's too big. So I'm thinking, all right, I'm gonna go with RF20. But I got to now look at to see if it'll do the job for 6,000 PSM. So I look down here. So if I go to the RF20 at 60 PSI, I'm 7,000. That actually gets the job done. I need 6,000, right? But we guerrilla engineer it because there's things happening in that confined space that I got to account for. You know, there's trays in the confined space. It's not just wide open. There's stuff happening in there, structures. So I'm gonna probably go with the 80 PSI. So that way it'll give me a free air volume of 11,000 CFM. Then I'm gonna field audit it once I install it. So finally, I'm gonna give them a design. I'm gonna tell them I'm gonna use the RF20. I'm gonna put it at M1, which is already all the way at the top, because I'm gonna take advantage of that natural tendency of hot air to rise, because I live in Louisiana and it's hot down there. I'm gonna use the swing gate because I'm gonna prevent short circuiting. Plus, if somebody's got to get out, remember that welder's up at the top, and it's probably easier for him to get out in an emergency through M1 than M2. So I'm gonna use that swing gate just in case something happens. Now I got to decide, am I gonna be negative or positive pressure in there? That's up to you guys to design. I'd say, would you say half of this, actually all of you guys said that you've only seen negative pressure. So you're gonna have that air coming out of the confined space, outward, negative pressure. So as we've seen, that's not really OSHA compliant, but it happens everywhere, except telecommunications and shipyards. I see positive pressure there. All right, I have a concern though, and I gotta go field audit. Do I have enough air, 6,000 CFM, moving at M3, M4, and M5? And if you remember, M5 is all the way at the bottom. So my worst case scenario is I'm gonna go to the bottom and check that out and see if I'm good to go down at the bottom. I'm gonna check the other ones, but should be good to go if the very furthest one from M1 is M5. If that one's good to go, it's probably good to go. And then you got to decide how you document and communicate this and what's your mechanism of doing that. And I've seen that a lot of people use Visio. They'll use PowerPoint. They'll just write it down. So however you guys decide at your facility to do this. Then I'm gonna go measure. Now, you know, this represents a pitot traverse where you're doing so many measurements. The reality is people go up to the manway and stick the anemometer there, get out of the way and see what the feet per minute is. You know, they're not doing it perfectly. That's just reality. But let's say I did it perfectly. And my average face velocity at M5 manway was 2,500 feet per minute. Remember, my manway is 24 inches. So if I figure out my cubic footage of that manway, multiply times my feet per minute, I'm left with 7,850 CFM. Remember, I needed 6,000, so I'm good to go. I field checked it. Now I just got to make sure no one messes with my stuff. Then I'll have people theoretically protected, but I got to go do my industrial hygiene sampling to make sure they're good to go. Yeah, and this is my little field note. Make sure that you buy an anemometer, velometer that goes over 5,000 feet per minute, or you'll have a problem typically. Your field audit, you got to go make sure that there's no contamination going into your makeup air. Make sure no one's messing around with your air. Make sure no one's hanging out by the exhaust of this confined space, because when they start busting refractory in there, it's going to be messy coming out of there. Maybe you put a sock on the exhaust of this, because all that air that potentially has silica in it's going to come out, and the sock can do a good job. But if you put a sock on it, you better go remeasure it, because that's a restriction. And you got to go remeasure it now, your manway. All right, so this is my resources. I have, I used a lot from Mike Harris's and company's Field Guidelines to Temporary Ventilation for Confined Space. Great, easy read if you're trying to learn how to do this. The Industrial Hygiene Ventilation Manual, all these OSHA different standards I used to put this together. And that's all I had. Y'all have any questions? Any questions on here also? And I kept it at 1 hour, so that's really good, yeah. All right, no questions? That's how good of a speaker I am.
That really was all.
All right, thank y'all.
Okay, let's take like 10 minutes and then we'll go ahead and jump into our class. I think I was supposed a little bit ahead of things.
What's that?
I think it is very good. Very good. Do a lot of ventilation work, so you know what's going on. I think I would you want to use a manometer for your ductwork weather?
So,
yeah, I know you get face velocity.
yeah,
Really,
you can use it, but I'm training industrial hygiene technicians and associates to do this in the field. So I found that it's easier for them to understand the anemometer, because we go do ventilation checks on lab hoods, so it's kind of a natural fit for them. The only time I'm using a manometer now is for asbestos.
All right, everyone, we're going to settle back in. We'll get time with the posters this afternoon or at lunch. And we've got our final speaker of the day. Mike, I'll let you take over. You can introduce yourself. I believe in you.
All right.
Okay, Dad. Oh, y'all gonna listen to Dr. Maple.
Well, I guess I'm the one that stands between everybody and lunch. So I'll try to make this pretty quick. I only have 136 slides to get through, so we should make it pretty well. So my name is Mike Callahan. I am not a CIH or a CSP. I'm a nurse. I'll tell you a little bit about myself here in a minute, but our objectives, we want to define what total worker health is. We want to discuss the impacts of that on the worker health, and then look at the benefits for both the workers and the employers. But really, you want to, we have to have objectives because we're teaching, right? But I'm more about the goals of it. So we want to introduce this new way of thinking to protect the employees and provide you with a way to get started. So about me, I'm a farm kid from Ohio, grew up throwing hogs around and plowing the fields, corn, soybeans, worked with the cattle a little bit. went into the United States Navy after that. I was a nuclear chemist, radiological controls technician on a fast attack submarine. Say that and get tongue tied. Then I got out of the Navy and became a firefighter. I was a professional firefighter paramedic in the city of Hamilton, Ohio. Then became a nurse for some reason. I thought that was going to be a great idea. I've been an emergency nurse for the last 20 years. I started when I was 3. At least I got a couple laughs, right? So I've been an emergency nurse for a while. You believe me? Yeah. So it was kind of interesting to me because both of the presentations before really apply to everything I've done. We get the respirator fit testing and stuff, you know, on the fire service, we wore SCBA masks and we would fit test and we had to keep our mustaches and beards trimmed. No beards, of course, because we're getting fit tested to wear these SCBAs. And that was always the big thing. We would trim our mustaches exactly where we had to so that we could still have them and be able to pass our fit tests, right? With the fire department, I was on the confined space rescue team. I worked on our heavy rescue unit for several years near the end of my career, and we did all of the confined space rescue. We used forced air, blowing it in for any of our rescues, by the way. We also had the respirators and those types of things as we were in there. I was also on Ohio Task Force 1. I was on the hazmat unit for Ohio Task Force 1. So with that, we wore all kinds of respiratory protection because you never knew what kind of crazy stuff we were going to get into. So it's very interesting that all of that stuff kind of tied into my fire department. Well, have you guys heard of COVID-19? I was an ER nurse during COVID-19. I took care of the very first COVID patient that came to Tuscaloosa, Alabama. I didn't even have a mask on, it's just coughing in my face. Somehow I didn't get COVID. I think I'm Superman. Probably. I haven't confirmed that, but I think I am. But anyway, we had no idea what was going on with COVID. And a lot of us were scared to death. I wasn't because I'm Superman, but my wife was. She's an ER nurse too. So we start wearing these N95 masks, or wearing the N95 masks all the time. You know how many people were actually fit tested for those? I was, but not everybody was. And then they came around and they said, oh, you wear a size regular? We've got extra large. Here you go. And then I wore the same N95 mask for like 3 weeks. And they said, well, we'll send it off and we'll shine a little light on it. And then you can wear the same thing. And we basically wore them until you couldn't wear them anymore. So the respiratory stuff all kind of kicked in. So then that goes all the way back to the first speaker who talked about COVID-19, right? And now, hopefully we're finally getting past the COVID-19, but something else is going to come. Something else will hit us. I work night shift. And this is usually what I look like getting off work. I used to have hair before I started teaching. And when I started teaching, you know, those nursing students just drive you nuts. So all my hair is gone now. But it really tied me into that total worker health piece, right? As I'm working night shift, especially on the full moon nights, we would get hammered the whole night long. You'd get off work and you were exhausted. 12 hours running around. We had acts of violence. I worked in the busiest trauma center in the state of Ohio, and every night we had to fight somebody. The police officers would bring the patients in. There'd be like 6 or 7 police officers on them, holding them down. They'd put them in the bed and they'd be like, you got it, and they'd leave. So now we've got a bunch of nurses fighting these same patients, right? Drug-induced, all these issues. So we started looking at just the physical work of that. I get off work, I didn't want to go to the gym and work out. I'm 12 hours, I might get to go to the bathroom once. And you want to talk about eating? No, there wasn't any eating. So I started thinking, what in the world can we do? How can I stay healthy as a nurse? So when we look at total worker health, It's policies, programs, and practices that integrate protection of work-related safety and health hazard with promotion of injury and illness prevention efforts to advance worker well-being. So you guys probably thinking, well, why in the world is a nurse here talking to me about occupational health and safety? I decided to go back and get my PhD. My PhD is in environmental and occupational health and safety through the University of Kentucky. I was part of the ERC there. Don't hold that against me because I know you guys are in the ERC up here. But I wanted my focus to be on biomechanics. Where that all comes from, I've been a personal trainer since 1994. I've trained everything from professional athletes to 80-year-old females. And we always focused on whatever they were wanting to do. So you guys have all heard the term industrial athlete, right? The common term for most. Industrial athlete is how we have to approach every bit of every one of our workers. We have to prepare them for what they're doing. Now, we have a football team over in Tuscaloosa. I don't know if you guys have ever heard of them, the Crimson Tide, Roll Tide, right? So I kind of consider myself the Nick Saban of total worker health, right? Only I'm much taller than Coach Saban. No offense to the Cal College down there. Sorry about that. But anyway, we start looking at these industrial athletes, and I have to prepare them for exactly what they're doing. If I've got an offensive lineman, their workout program is going to look a lot different than a wide receiver, right? So if I've got somebody, a frontline factory worker, that's having to lift and move things, that's going to look differently than someone that's in an office all day long, right? Our diet plan, our meal plan, everything's going to look different. So if we really start looking at the scope of the problem, I know these are slightly outdated statistics, but they're pretty close to current data. 14 people die each day from a work-related injury. 2.8 million people get injured at work each year, 430,000 occupational illnesses. It's a pretty big deal, right? I'm scared to death of heights, so you would never find me up here. Even though I was on the rope rescue team and I've jumped out of helicopters and airplanes and stuff, I'm scared to death of heights. So I will not go up there. You need me to survey something up there? No, sorry, I'll find a new job, right?
Hey, yo, I think we lost audio on the virtual section. It looks like it may have been muted on accident. Maybe, I'm not sure.
You guys actually laugh every time when I tell my jokes. Can you hear me now online?
Perfect, thank you.
All right. So we start looking at heat and how that exertion really takes off with the person. So I'm currently IRB approved yesterday, finally, looking at how heat impacts cognitive functioning. I'm using a nursing population for that. Well, how does cognitive functioning work around occupational health and safety? One of the #1 causes for injury on the job site is human error. So if my cognition is not there, then I'm going to have human errors and I'm going to end up getting hurt, right? I think all of us know a story of somebody that just wasn't thinking right and did something stupid. Typically it's males, you know, in the trauma field that I normally work in, it's usually here, hold my beer, watch this, you know, and it's usually a male that does something stupid. I've been that guy, that's me. But we see that a lot. we're also trying to tie that into cardiovascular functioning. So as we continue to build, we want to see what heat does to the cardiovascular system. We want to see what those inflammatory markers look like. We want to keep progressing this. So heat's our real focus right now through our Total Worker Health Center, or not center, affiliate. So this is actually a friend of mine that was injured on the job. This is Doug. I was working in the emergency department with Doug's girlfriend one day. Doug was out he was the police officer that was escorting a funeral through town. Car decided to run Doug off the road. Doug broke his arm, as you can see. So I'm standing there in the ER and my cell phone rings and it's Doug. And I'm like, hey, Doug, what's going on? And I can hear sirens in the background. So, oh, nothing. What are you up to? Well, I'm at work. He goes, yeah, my girlfriend there. Yeah, you need to talk to her? He goes, no, I need you to talk to her. What's up? I was like, well, I was in an accident and Dayton Fire Department's bringing me into the hospital right now. He's like, I'm okay. I'm okay. And then he continues to tell me this story of him getting run off the road, and here he is. This is an occupational injury, right? How many times have you seen something like this on the job site? I know some of you have never seen stuff like this, but it happens, right? We get these musculoskeletal injuries, we get other soft tissue damage that we're going to see. And we have to know how to respond to this. We have to take care of this. Doug was laid up for about 6 months from this accident. Think about what that does to his family. Think about what that does to the total picture of Doug's health. Yeah, his productivity was nothing while he was gone. But there's more to our employees than just how productive they are at the workplace, right? Typically, we have a work-centered approach to safety. Is everybody familiar with the Heinrich domino theory from 1930s? We start with a social environment, typically a fault of a person. We get an unsafe act or an accident, and that leads to an injury. Okay, this is tying into everything we know about total worker health. That heat issue. If I'm not able to concentrate, I'm going to have an accident. If I'm sleep deprived, I'll have an accident. If I'm overly fatigued, if I haven't eaten, all these issues build right into total worker health, which is why there's now been a new focus on total worker health. Because we're seeing the whole picture of the person. We have the engineering controls, and a lot of the incidents we see are those bad accidents, right? A fatality, you're gonna have everybody coming into your workplace. We had an on-the-job near miss. I was the instructor on a river rescue exercise, and we had a firefighter that was pinned underwater for 26 minutes. Good friend of mine, and we're standing there, we're looking at him. He's pinned in a Lowhead Dam. And every single one of us were just, what are we going to do? This is one of ours. We were at the point that we were going to jump in the water above the dam with a rope tied to us and try to flush over so we could grab him. Somehow we got Chris out. It wasn't anything we did. As we pulled the other boat out, he was actually still tangled up with that other boat. So we got him out. He is still working as a firefighter. He's driving a fire truck now. Still dumb as a box of hair, but he started that way, so it didn't really change any of his cognition. But it impacted every one of us on that job. Every one of us. And then when we had to get back in the water, I made sure I was one of the first ones back in the water because we did something, our process was wrong and it hurt somebody. So that impacted everybody. But how many times have somebody just sprained an ankle, or somebody is, they're just not feeling right, they're not feeling well. Those near misses that never get reported, that we never look at. So we have to look at all of those pieces when we start talking about worker health. How many of us have stood on the top of a step ladder to work overhead? I did that this weekend. Somehow I didn't die, fortunately. I trusted my wife to hold the ladder. I'm glad she wasn't mad at me because, you know, one little shake and I'd have been toast. But we look at these behaviors. We see something crazy like this and we're like, hey, I know that that's a problem. It's easy to recognize that is a problem, right? Not always easy to know that he didn't get any sleep last night. He hasn't really been eating very much because, hey, they don't have a lot of money. You know, these lower income employees sometimes are working 2 or 3 jobs. So they don't get the sleep. They don't get the rest that they need outside of the workplace. They can't afford the food that they need to truly have a good diet. So we think we're going to do some worker training. I've sat through many training sessions where my mind was not there. I'm exhausted. I just want to get through because I know that, yeah, we're getting a 1-hour training. I have an 8-hour workday. They still expect me to get 8 hours worth of work out of me. We start looking at that safety coaching. I worked in a sheet metal fabrication plant, and I hated when our safety guy would come out and try to tell us what to do. We would tune them out. We would ignore it because we knew he was going to go back in his air-conditioned office and we were going to still be out there working. How do we get over these markers? How do we get over these things? Hierarchy of controls. Everybody recognizes these hierarchies of control, right? This also is going to apply to total worker health. So if I look at elimination of that hazard, if I can give my workers some time to actually recuperate, if I can give them time to actually eat, if I can take some of that stress off, I'm eliminating those factors, right? Substitutions, the engineering controls, administrative controls, things that we can change, and then PPE. Anybody see any problems with this? A friend of mine called me the other day and she's like, I can't get my electric chainsaw to work. So like, and I took it into the shop and they were going to look at it and they just laughed at me and, you know, they made me feel like I was stupid. Like, oh, well, bring it to me. I'll take a look at it. The chain brake was on. This is why it wouldn't work. A lot of times it is those simple things, right? But we have to train people. This guy has obviously never used the chainsaw before, or just doesn't want to have children. Either way, I'm not going to judge him. But it's easy for us to look at these things and pick them out, right? What's going on in his mind?
Nothing.
Well, does he have distractions? Does he have a sick kid at home? Did his wife just leave him because he's an idiot? You know?
He's got to kill a deer or something.
Right. I mean, there's something that we're missing with this picture. Start looking at a systems approach. So we're going to have policies. There are policies everywhere that I'm sure everybody reads every single policy, right? We got checklists. Does everybody love a checklist? Nothing like sitting down to read a good checklist. Right? We go through and we're checking these things off. Hazard analysis. Again, it's our previous guy. It's easy for me to do a hazard analysis on this. Safety management, integration of those quality programs. So looking deeper than just what we're seeing of those hazards, what's that person going through? What's our employee actually, their lived experience right now? So we start thinking about why is total worker health important? Why is total worker health important to any of you guys?
If you take care of your worker, you produce
reduce, it's more production from a, I guess, a company standpoint, but if you take care of the worker, they'll take care of you, in short. And I mean, they're humans. You have to take care of them. They have to take care of them.
Right. So if we take care of the worker, then we take care of, we are in turn actually helping our business, our productivity.
It's their right.
That's their right. We need to protect our people. And if we think about it, the end of the day, everybody needs to go home safe, right? But we also want them to go home and be able to spend some time with their family. We've all gotten off work and been so exhausted, we go straight to bed. You sleep until it's time to get back up and go to work. What kind of life is that? Does anybody know anybody that gave 40 years to a company, they retire in 2 weeks, they fell over dead? Yeah, we see that a lot. We want to extend that longevity of our workers, not just for the production of the company, but because they're human. These are people. We want them to have a life outside of the workplace. Everybody heard of the social determinants of health? So we start looking at the social determinants of health, and they come into play with every aspect of total worker health. So economic stability, that becomes a big issue. Our lower wage earners, a lot of them are working 2 and 3 jobs just to have some sort of economic stability. We have to consider that. Access to education. Are we training our workers up? Are we giving them a potential inside the company to expand? How do you think that plays on us psychologically? If I know I'm stuck doing the low-end jobs, what kind of production am I going to do? What kind of drive do I have to get better, to better myself and in turn better the company? We do hear those success stories of people come in at the bottom, sweeping the floor, and then next thing you know, they're CEO. Those are pathways that we can help to address. This building a neighborhood and community, this gives that life outside of work. This gives them some reason to continue on, right? It also builds a community at work. Recently just finished up a PTSD study among emergency nurses. Every single one of them said that their best part of going to work was the team, the community, the family that they had at work. And I'll tell you that emergency workers, we go through a lot of stuff. I found out on Saturday that a good friend of mine that I worked with for 10 years while I was at the fire department fell prey to his demons last weekend. We're doing his ceremony next Friday. It's something that's real. That's the total worker health. This guy was a great firefighter, retired from the fire service. Stuff still caught up to him. We failed Kenny because we didn't look at his total health. We didn't look at that psychological side. But how many of us, when we're looking at our employees, think about their psychological side? All comes into play. Access to healthcare. Yes, employee may have health insurance, but they work 8 to 5. When do they have time to go to the doctor for a checkup? You know, do we make them take some of their vacation days to go see the doctor? These are all issues and concerns that we have. Uh-oh, I'm locked up. There we go. So when we start looking at any of our injury processes, we have to start thinking along this line with it as well, right? So we've got the healthcare. Do we know the health history of our workers? You know, a worker that has diabetes has different issues that we have to be concerned with than someone that doesn't have diabetes. someone with congestive heart failure, someone with high blood pressure. These are all concerns. And that's not even getting into the medications that they take. I mean, some of these medications will say to avoid exposure to heat. They'll tell you not to operate heavy equipment, right? So a lot of these medications, they need to be known. We need to know so we can personalize the protection of that employee. We start looking at other things, tobacco use, diet and exercise, alcohol use, sexual activity. All those pieces come into play in the workplace. I know a lot of people that started smoking because they could get a smoke break. You know, there was a lot of nurses that did that because, hey, you get a break every hour because you're a smoker and I have to stay here on the lawn. I'm gonna start smoking so that I can get that same break. And you would think that that's counterintuitive, but a lot of people did it. The alcohol use, of course, we talk about it all the time in our heat safety class that we do. When I'm working around the house, I'd get me a nice cold beer. It cools everything off, right? It's actually worse. I can remember when I was a construction worker, 20 years old, young and dumb, out on the job site, the roach coach that would come around, everybody knows what a roach coach is. So they actually bring food to the job site. Well, the roach coach had beer on it. It was awesome. Our supervisor was like, yeah, it's okay if you guys have a beer. It's just one beer. So we'd have a beer in the morning for the morning break, drink a beer or two at lunch because of course it's lunchtime, you had to have beer. And then we drink another beer, for the afternoon break. I mean, we were feeling good by the end of the day. But you can see where that's causing a lot of problems on a job site. Because we used to set 15 feet high by 20 feet walls, concrete walls. And we're out there slightly impaired. It wasn't too smart of us, right? Again, young, dumb. Total violation, don't go back and tell them at the office. Total violation of what things are doing. It also impacted our tolerance to the heat because alcohol has a negative impact on heat. So, I mean, my tolerance was through the roof at that point, but it was still impacting me heat-wise, impacting me otherwise. We get in that physical environment. Then we started looking at things like education, job status, family support, income, community safety. All of these pieces come into play and are going through our workers' minds while they're on the job site. How am I going to pay that bill? I got to get my kid to the doctor. I got to get my kid to baseball. I mean, I think anybody that's got young kids knows the schedule is probably worse outside of work than it is in work, especially when they start playing sports. So we look at the job-related factors that come into play with the total worker health. Wages, of course, is going to be an indicator. So I'm not saying we need to increase minimum wage. That's all. I'm outside of all of that, but we need to give them a path to make their way up, right? Give them something to work towards. Work hours. I said I was night shift nurse. We worked 12-hour shifts. And a lot of times we got held over. Now, night shift, I'd have to drive home after night shift. I lived an hour away from the hospital. I chose to live an hour away. After you've been up all night and you go to drive, unsafe, right? So we got the unsafe conditions of driving. Plus, when we look at errors in the hospital, a majority of them happen in the last 2 hours of the shift. So long work hours really do throw off our schedule. And I'd say everybody in here has worked those 10, 12-hour days or longer. I can remember in the Navy on the submarine, we had a part that failed on our evaporator, and there were only 3 of us that knew how to machine parts. And we stayed up in a matter of 6 days. I think I got 6 hours of sleep. And that was how all 3 of us were doing, because we were watch and then working, trying to get this piece of equipment repaired, because we had to be able to stay out to sea. And if you don't have fresh water, You can't stay out to sea. But those are the conditions that we put ourselves in and we put our employees in sometimes. We start looking at the interactions at work. Do you actually have that camaraderie? You know, some job sites, it's a little more difficult than others. In the emergency department, I'm surrounded by other nurses. When I go into the university to work, I go in my office and shut the door. A lot of times I don't interact with anybody. What's that do for your mental health? I mean, look at how crazy it's made me. So, I mean, these are things that we have to take into consideration. And then that paid leave. Do I have time to actually even go to the doctor? Do I have time to do the things I need to do? We start looking at how this stuff actually impacts the worker. So obesity is a huge issue in the United States. I've seen upwards of like 50% of the workforce in the United States have obesity. And anytime you look at any medical condition, obesity, sedentary lifestyle, stress, these are all the big issues that lead to these medical problems, right? If you think about a physically demanding job, when I spend 12 hours in the emergency department, I did not want to go to the gym after work. I did not want to go home and fix a nice healthy meal before going into work. If I'm working 3 days in a row, how am I eating nutritiously? How am I getting any exercise outside of the workplace? So all things we got to start considering. When I worked in the factory, we would have these deadlines, time frames we had to have. And I'd get to work at 3 in the morning and I'd stay until 8 o'clock at night. And then right back in the next day. And that happens in workplaces all across the country. I'm not alone in doing that. I'm sure a lot of you sitting here have done those same hours. These are things we have to consider. Because now I start getting that obesity. That's going to lead to my cardiovascular disease. Started working with firefighters for some of our research. Number one cause of death for firefighters is cardiovascular disease. Most people wouldn't think that that would be the cause. They're going into burning buildings, they're going into all these dangerous situations, and cardiovascular disease is their killer. A lot of things come into play, right? We start looking at mental health aspects of things. So as I said, I just lost a friend last weekend. Since getting out of the military, I've had 12 friends that have taken their own lives. That's a lot of people. We're failing on the mental health side of things. Musculoskeletal injury, that was kind of my bread and butter. That was my baby, right? I wanted to look at musculoskeletal injury. But I can't just look at musculoskeletal injury. If you're not getting a proper diet, you're not getting good rest, you're doing all these other things of risk, musculoskeletal injury is going to happen. And it's just something we can't prevent. So what can this do for me? So this young lady is actually, I think she's 74 years old in this picture. And she's doing deadlifts. Have you ever seen a weight room in a nursing home? No, because people stay active, right? Physical fitness. When I owned a gym in Ohio, and I had an 83-year-old lady that would come in 3 days a week, and all she wanted to do was this. She was a farmer. She grew up on a farm. She lived on the farm the whole time. They turned the business over to her family. And she would come in and she goes, I just want to live. Anybody be offended if I say a cuss word here? Because I'm quoting someone. She goes, I just want to lift heavy shit. And it's from an 83-year-old woman. And I said, I get it. I get it. And she would come in, she'd put on her big socks. She had all her hand wraps and her little pink belt. She'd go over there and she'd just lift heavy shit. And I said, that's awesome. And that's what we want our employees, right? We want our employees to be able to have that extended work life. We want them to have an extended life. I want them to be able to go home and still play with their kids. I want my employees to be able to go out and still have a good time. Because I don't think anybody says, I relieve my stress by going to work. Well, maybe some married people do, but that's not typically the response, right? It's not usually, oh, well, how do you relieve stress? Well, I go in and I work a 12-hour shift and, I push myself to the limit. I don't do that. It's outside of work. And if I can get out of work and recharge, when I get back to work, I can be more effective, right? I'm going to be more productive. I'm going to have more energy. I'm going to relieve stress. How do you guys relieve stress? Study for an exam? I create a nice poster about a research study that I did to relieve all my stress. Right? That's some of the worst stuff ever, right? That's horrible. Nobody likes to do that. That's not a stress relief. Stress relief, I go out and I take a walk. I go to the gym and exercise. I spend time with my family. We have to start considering this stuff when we start looking at the health of that employee, the total worker health. So it's about changing the design of work to promote well-being. Have you guys ever seen a workplace well-being activities? It's usually the office workers or the higher paid employees that are participating in that. A lot of the statistics say that the people we really need to reach, the frontline workers, they're not actually participating in any of those things because they're too busy doing the work. We need to change that dynamic. We need to change it up and actually get this out to our lower wage earning employees. That's me, I'm Big Bird. Try to have that energy, right? You guys ever work with somebody that's always happy? I've worked with a few of them. They're usually pediatric nurses, but that high energy, that keep going. I know that one of the people I work with at University of Alabama over in Safe State has more energy than anyone I've ever met. And I've met a lot of people on crack. But he's got a lot of energy, always doing something. But that always helps motivate people. It pushes everybody around them. Be Big Bird. I mean, I like Darth Vader, and my wife tries to force choke me all the time, but be Big Bird. Change things up at work. Make everybody around you better. So the attributes we look at work itself. We have to look in the workplace. We have to look at those injuries. We have to look at those dangerous activities. There's risk in any job that you do. We have to look at that. We have to engineer. We have to have the best controls. We want to look at voluntary participatory health interventions. You and I both know that if I say, hey, we're going to have a health meeting after work, if you guys want to show up, most of our employees ain't going to show up. Right, but we want to get them involved. If I come in and I say, hey, you have to start going to the gym. Sorry, you just got to do it. Not going to do it. So we have to figure out ways to actually get people to want to participate in these things. We have to have that incentive there. We have to protect workers' privacy. We start talking about health conditions and medical conditions and medications, that falls under HIPAA guidelines, right? We have to be able to protect that stuff. But if we don't know all that information, how can we protect the worker? So we have to have some type of system in place to help protect those workers. Total worker health does not blame the worker. I know I get a lot of kickback because I say nurses need to learn how to move better. We're one of the most injured occupations out there. We need to learn proper lifting techniques. People say, well, lifting techniques don't work. So, well, your The mechanical lift doesn't work if I use it improperly. If I don't position myself properly, then it's not going to work. So but we have to take that blame from the worker. I can't blame the worker for it. I have to understand all these limiting factors as to why the worker can't do all these things. And then provide a means to help them to be better. It's not just about healthcare, health insurance. It's about actually allowing the employee to experience the health, that preventative medicine. All of those attributes have to come into play. Like I said before, participation in a lot of this stuff is blunted because that low wage worker that has health insurance, but I don't give them any time to go to the doctor for preventative medicine, they have to use their vacation time to do that. That's not in the well-being of our employee. So the past model was always everyone goes home the same way they came to work. What we're trying to move toward is that people go home, but they go home better. They go home in a better position. They're better equipped to live the life. So we have to collaborate with the employers to really build that culture of health. It's easy for me to stand back here and say, hey, we need to give our employees time off work. But how do you do that? You know, I tell my nursing students, it's easy for me to sit in my ivory palace in academia and try to dictate what's going on out in the real world, but that's not always possible. So how do we collaborate together to work for the best of our employees? How do I build those health programs and policies? How can I do all of that? So we talk a lot about team building. In the heat class that I teach, we always ask, who are you going to have on your team? Who do you want on your team? And people are like, I need this expert, this expert, this expert. I said, no, you need that worker because they can get in there. We need to pull the HR representatives in. We need to pull management in. We need to pull workers in. It's easy to sit in an office and dictate what everybody else does. But to make something that's actually going to work, we have to have that collaboration across the disciplines. So for the success of the Total Worker Health program, you have to have a shared commitment to health, safety, and well-being. OSHA sets guidelines, and if you go out into the shop and you don't have that safety device on your machine, you're going to get fined. State laws mandate break times. But are we really giving them the break? Yeah, you got a break, but you still have to meet your numbers. You got to make sure we're committing to it, not just putting it on paper, but committing to the health and the well-being of our employees. We've got to have that support all the way up to structure. Got to start looking at responsible business decision-making. I think we all, as we saw COVID coming through, saw that we had to change up the models that we were using, change up the way we did things. We still have to continue that. We have to keep it going to make sure that we're looking out for the health and the well-being of our workers. We have to give meaningful work. We have to give a purpose. And then giving that respect to the workers. It's easy to just label someone. Oh, there's the janitor. One of the questions on the first test that I do for my nursing students, what's the name of the janitor? What's their name? Because every single person in that business is required to keep that business going. And for them to function at their top is what's going to be needed for the most productivity in that business. So, but in the end, total worker health is my job. And it's your job. We have to make sure that we're continuing to take care of our employees. Some of the interventions that we'll see, workplace, I mean, I think every workplace has a tobacco cessation policy or some type of program that employees can go to. Start looking at healthy eating. And this can just be giving access to a refrigerator and a microwave. And if I give 30 minutes for lunch break and I've got 50 employees and I've got one microwave, do I have enough resources for my workers to get a healthy meal, to actually get to sit down and take a break? So these are things we have to consider. The employer says, well, I provide you this stuff. We don't provide enough, right? Substance abuse counseling, or stress reduction programs. In healthcare, we've gotten really good at doing the stress reduction stuff. So there's all kinds of different programs, different counselors that you can talk to, all of those pieces. But in general industry, we don't have that. So those are all things we need to do. Emergency childcare. Anybody see that as a problem with COVID? We had a lot of, like, all the daycares around were closed down and the kids were home from school. So how can I expect my workers to come in and leave their first grader at home by themselves? These are all things we have to be cognizant of. Now, COVID was the extreme, but we still see that every day where workers' kids will get sick and they have to miss work. How do we provide some type of wiggle room in there for that? How do we prevent sleep deprivation? You know, how can we make sure that our workers are being able to sleep? Those low-income workers, remember, they're working 2 or 3 jobs. So how can we build those things in? Fitness programs. With the fire department, it was awesome because I had a gym at the station. I could go work out on shift and it was awesome. I can't do that at every job. Can't do that when I'm at the hospital. So how can we build some programs in? Another thing with fitness programs, a lot of employers will provide a gym membership, but how many of you know how to use gym equipment and would be comfortable going in and creating your own workout program? That's an issue. It's an issue, right? So why can't we provide some of that extra training piece? Why can't we go a little deeper with it? We'll really get the benefit out of the programming then, right? We start looking at weight management programs. A lot of times, if we just get our workers into being able to use some fitness stuff and give them time to eat appropriately, weight management is going to take care of itself, right? And then these chronic disease preventions. We start talking about respirators, we start talking about confined space injuries, we start talking about any of these chemicals and toxins that are on our workplace, we focus in on them. But what about the other things? What about diabetes? What about congestive heart failure or high blood pressure, those stress levels? All these issues that we can try to bring into play when we're talking with our patients or our workers. So a few little take-home pieces. And bottom line, we're not going to fix total worker health overnight. This is going to be a culture change. And culture is something that takes time to evolve. And each one of us can add to that. But total worker health does have a benefit to everyone involved. The workers, the employers, the communities that they all live in. Total worker health programs must be designed that they can reach those at the greatest risk. Those low wage earners have to be pulled into these total worker health programs. We can't just do it to say that we have something on paper. We have to actually do something meaningful. And then total worker health programs do increase or improve the outcomes for the business. We have more productive workers, less days missed of work, and just a happier environment. So that is the end of my 137 slide presentation. Questions? Yes.